So last time we expressed the momentum wave function in the position basis, and we did it in this way: psi sub p of x. I'm going to put a little squiggle over the psi sub p so we distinguish it from psi. Psi sub p of x is equal to 1 over the square root of 2 pi e to the I px over h bar. Let's do the following. Let's take inner products. Let's take the inner product of x and p. I can write that as 1 over the square root of 2 pi e to the I px over h bar. By the same token, I can write the inner product of p and x as 1 over 2 pi square root e to the minus I px over h bar. The momentum wave function has a form of sines and cosine waves. So the wavelength of the function e to the I px over h bar is given by lambda is equal to 2 pi h bar over p. Now, notice, since the function is unchanged, anytime we add 2 pi h bar over p to the variable x, since it's periodic, notice what happens. E to the I px over h bar. And let's do this. Let's write it as e to the I over h bar times p x plus 2 pi h bar over p. This is just like writing e to the I px over h bar times e to the 2 pi I. This, of course, is just 1. So we're not changing anything by adding values of lambda. Therefore, I can write this as just e to the I px over h bar. Now we might ask ourselves, what's the probability that a particle has momentum p if it's measured? Well, we might say p of p is equal to p psi squared, just as we did before, probability that we have p. We can say that p psi is just the wave function of momentum in momentum representation. So now we're not in the x representation, we're in the momentum representation. And we can write that psi sub p, I should say psi of p, is equal to p hat psi. So I can represent a state vector, psi, in the position basis, or I can represent it in the momentum basis. Both psi of x and psi squiggle of p, or psi tilde of p, represent the same exact state vector psi, but it's just a different basis. And of course, now what we want to do is figure out how to transfer between momentum basis and position basis. And the way we do that is we learn a trick. The trick is called resolving the identity. How do I do that? What do I mean by that? I'm going to define an orthonormal basis of states through the eigenvectors of some Hermitian observable. Let's call the basis vectors I. I'm going to write the identity operator I as a sum over I I cat times I bra. Now, both position and momentum each define basis vectors, and I can do the same sort of resolving in this way. I can write my identity operator, as integral of dx x x. Or I can write it as I is equal to the integral of dp p and p. So suppose we know psi in the position representation. So suppose we know that psi can be written as x capital psi cat. Let's find it in the momentum representation. So first I write psi tilde of p is equal to p psi. And I'm going to write that as the integral of dx px x psi. See, what I've done is I've inserted in here the identity operator. I'm representing the identity operator by this sort of reversed inner product of x and x. Now, x psi is just psi of x, and px, as we had before, is 1 over 2 pi square root e to the minus I px over h bar. So I can write psi tilde of p as 1 over the square root of 2 pi times the integral dx e to the minus I px over h bar times psi of x. Now I can just as easily go the other way. If I know psi of p, psi tilde of p, but I want psi of x, I can just say, well, psi of x is equal to x cat psi. And I can write that as the integral of dp times e to the I, dp x p psi. This, of course, is e to the I px over h bar. This is just psi tilde of p. And so psi of x then is 1 over square root 2 pi dp e to the I px over h bar psi tilde of p. See, they're reciprocal Fourier transforms of one another, x and p. Pretty nice. So we can go from one representation to the other simply by taking a Fourier transform. Now let's look at the commutators. X psi of x, I can write as x times psi of x. P operating on psi of x, I can write as minus I h bar d psi of x dx. So I look at commutators. If I do x p psi of x, I get minus I h bar x d psi of x dx. But if I do px operating on psi of x, look what I get. I get minus I h bar d of x psi of x dx. I got to employ the chain rule, and this gives me minus I h bar x d psi dx minus I h bar psi of x. So if I take the commutator, if I do x comma p, I got to subtract, that's just equal to xp minus px. And it turns out it's not 0. It turns out I have an extra factor of IH bar remaining. That tells me x and p do not commute. It's not possible to find simultaneous eigenvectors for two non-commuting observables. You can't find two simultaneous eigenfunctions or eigenvectors for momentum and position. What that means is that you cannot simultaneously ascertain momentum and position. Remember the expression we did for the generalized uncertainty principle? Watch what happens here. What we had before was 1/2 psi commutator AB psi. If I put in my expressions for, instead of using A and B, I use momentum and position, I get 1/2 psi x p psi, or delta x delta p must be greater than or equal to, if I put my commutator as IH bar, it's going to be greater than or equal to H bar over 2. Watch this. Look at it a different way. Suppose I find the probability in momentum space of having position x. Look what I get. I just get 1 over 2 pi. I get a completely uniform result. There's no peaks, there are no valleys. It tells me that a state with definite momentum can be anywhere position-wise. If you know the momentum exactly, you have absolutely no idea where the particle is, in other words. That sort of culminates what I want to do in terms of the preliminaries for, let's say, a linear algebra approach to quantum mechanics. What I'd like to do next is to do the sort of hardcore solutions to the Schrodinger equation for different potentials. And we'll pick up with that next time.